All right. Hi, everyone. I'm Sean. Thanks for coming. A little bit about me. I'm apparently the only Canadian who can spend a week in San Francisco and catch a cold wearing a t-shirt, so we're just going to have to suffer through this together. I was going to bring some booze and make everyone drink every time I sneeze or say continuous integration, but it turns out I can't bring that much alcohol over the border. Funny that. It says up there that I'm here to talk about continuous integration for Spark apps, but what I'm really here to touch on is the gap between writing scripts for Spark and writing software for Spark, because they're not really the same thing. I work at a company called Uncharted Software, which does a lot of work in the big data and visual analytics space, so naturally we use Spark a fair bit. We write libraries for Spark, some of which are open source, and we integrate it into many of our applications as well, but we always run into the same problem. It's really hard to test Spark software. And before we jump into why, let's talk a little bit about what I mean when I say Spark software and why would I actually want to test it. Although I hope the previous talk touched on that a little bit as well. So case study. Here's one of the libraries I've been working on. It's called Spark Pipe. It's a nonlinear data pipelining framework which is designed to make it easier to create reliable, reusable, and modular Spark code, which can be shared between teams. It includes core operations, which reduce boilerplate code, and is also designed to allow the creation of standardized interfaces, which increase compatibility between our various Spark libraries, and we hope others in the future as well. We're in the process of open sourcing this right now, so check it out on GitHub if it interests you, or we can talk after. But the important part is that given that it's a library that's being relied upon by several teams in my company, some issues arose immediately. One, we really needed to make sure that it's reliable. In particular, the core operations included with the pipeline need to do what they say. Two, we have to prevent regressions as we grow the library of operations. Three, we want to maintain compatibility with several versions of Spark. And four, it's an open source project, and I need a good way to evaluate PRs, and that's really where continuous integration comes in for us. So what's continuous integration? For those of you who aren't familiar with the practice, let's start with a little definition. Here's what some folks at ThoughtWorks have to say, but I'm pretty content to simplify the expression to something more like that, but that's just me. Let's get a more useful definition. We'll start with some best practices that I've expertly harvested from Wikipedia. Number one, maintain a code repository. For us, that's Git. For you, that's probably also Git. Two, automate the build. We use Gradle for that. Most of our libraries are Scala libraries, so this is going to kind of be a Scala-oriented talk, but I hope that it's kind of broadly applicable. Tests should be part of the build. That means they should run when you build your code. We use ScalaTest for this. Commit and push your feature branches often. Do it for the children, please. Five, build and test all the branches. If you're using a development workflow that involves feature branches, and you probably should be, it's important to test each of them in isolation to evaluate whether or not to merge them into your final product or a release. Six, test in a clone of a production environment. Don't forget this one. It's probably the most important one that I'm going to be talking about today. Seven, keep the builds fast, at least do your best anyway. And eight, everyone must be able to see the results of the build. It's important to have visibility into the results of branch builds so that developers make good decisions and make them early. So I'm going to go out on a limb here and assume most people are doing this much with their Spark applications. But this part is significantly less trivial. So when I said before that it's really hard to test Spark apps, these four things are what I was really talking about. And to understand why they're hard, let's take a step back and ask ourselves, what is a Spark application? It's that thing. It's a Java archive which gets submitted to the Spark cluster, a runtime environment, and it runs there in a magically distributed fashion and produces some kind of output. And what we really need to do is test our app inside the Spark environment because it probably uses Spark runtime and libraries. And two, we need to run it in a distributed environment to detect nasty things like closure serialization issues and other potential runtime exceptions that are unique to the Spark environment. But unfortunately, unit testing frameworks like ScalaTest spin up their own Scala runtime environment and test the code there instead of in Spark. So it's probably not going to work out of the box because at the very least the Spark libraries aren't present. And at best we can do what the Spark project does to test itself, which is V1. They include the Spark libraries and they create a Spark context within the ScalaTest environment and they use it to test code which needs a context. This is roughly equivalent to submitting the code to a standalone cluster. Unfortunately, it's not quite the same thing. For instance, if I were to create an RDD with sc.parallelize, it's going to automatically partition that RDD into one partition. This makes it difficult to test merge code within a custom accumulator or code using combine by key. And it's really up to me to be smart enough to manually repartition things to address this and get good code coverage. Code which doesn't use a Spark context won't really be tested in Spark. It's just going to be tested using whatever version of Scala you have on your machine, and it's really up to you as a developer to keep that in line with the version of Spark and Scala that you're targeting. So in summary, it works, but only sort of. And we fail test number 6. We're not testing in a clone in our production environment. What we really need to do is run our test suite inside Spark. So let's try something a little crazy. Let's make our tests into a Spark application. Turns out it's relatively easy to package your tests up in a jar alongside your distribution jar, which contains the code that you're trying to test. To be useful, all it actually needs is a really simple main class, which kicks off detecting and running all the tests in the bundle. So if we put our distribution jar on the path and Spark submit our test jar as an application, our tests will actually run inside the Spark runtime. They'll produce output on standard out, and they'll stop with an accurate exit code, which reflects the status of our tests. Have a peek at main.scala. It's a very simple Scala object that uses the ScalaTest runner. We use the -o flag for standard output instead of graphical output. Honestly, don't ask me why graphical is the default. That's insane. And we exit with an error code if something goes wrong. So at this point, you're actually good. If you have a Spark cluster, and you probably do, you can Spark submit both jars and run main.scala in Spark. You'd actually see the output of your tests right there as output of the Spark application, and we've effectively turned our tests into a Spark application. And we can give ourselves a sweet little check mark on number 6. But that's not good enough. Let's have a look at number 5 and 7. In particular, we need a way to build and test our branches automatically as we commit code. This is commonly referred to as a continuous integration system. The problem is that our CI system needs a Spark cluster to actually submit this test jar to. And in reality, it needs a fresh cluster every time to submit each branch to so that the tests run in complete isolation. We can achieve this by creating a small Spark standalone cluster within a Docker environment and wrap up our entire build process in there. The good news is I've already done this part for you. We've released a base container called Uncharted Sparklet, which contains a small Spark standalone cluster with 2 workers and 1 master. For those of you who are not super familiar with Docker, think of it as a way of sandboxing a process completely from an operating system and giving it a virtual file system while sharing its kernel. It takes the place of a lightweight VM without any actual virtualization going on. So we can build our code in that container, Spark submit it to the cluster inside the container, and have the output and exit code of the container be the output and exit code of Spark submit, and thus the build process as well. You can fire up 1 container per branch and tear them down as your tests finish and your builds are over. This turns the process of testing a Spark application into the process of testing Docker containers, which is actually a lot easier to solve, it turns out. And we'll get to that in just a second. Have a look at how we run the container. It involves a horrifyingly long Docker run command, which I often throw into a shell script for the sake of simplicity. Most Docker run commands are horrifying though, so this is pretty par for the course. The important part here is that we're mounting our source in as a volume, a shared volume, so that we don't actually need to build a new container every time we change our source code. This helps speed up the build. It selects the version of Sparklet based on an environment variable which matches the version of Spark, and we test against that using Gradle W test. Looking at the relevant Gradle task, which builds everything, it pretty much just runs the build and submits the code to the test container inside Sparklet in 1 command. There's really nothing fancy going on here. It depends on jar and test jar, and it submits our code via Spark submit. So now we have a container that can run our test suite against a real Spark cluster, print the results and of the tests, and exit with the correct exit code. The problem becomes we have to test the Spark container. There's an interesting sidebar here, though, if you give me a minute. The same container can actually be used interactively by developers as well on their own machine, so that they can rapidly test code as they develop in an identical environment to the CI environment. So our developers don't actually need to install Spark, they don't need to install the JRE, they don't have to maintain compatible versions of Scala or anything like that, and it really helps new developers ramp up really quickly. If you want to know more about this, I can show you after the talk, and I'd be happy to give you a look. So approach number 3 gives us an extra check mark for best practice number 6, and 1 for number 7 as well, since the container image is cached and comes prepackaged with Spark. In order to achieve number 5, though, we need a way to test our container in an automated fashion. The good news is Travis CI, a popular CI system, supports Docker. Jenkins and Bamboo do as well, incidentally, but SparkPipe is open source, so we chose Travis. All you need to do to make it work is use a Travis config file, which looks like this one. It looks a lot more complicated than it actually is. The entire before script section, pretty much most of the left side of the screen there, is just extracting environment variables from the Travis VM that's running in the cloud, and it just passes those variables into the Docker container so that my build actually knows that it's running in Travis. This is important if you're using any Travis-related Gradle tasks and plugins. When we run the test container in the script section over there, we're using essentially the same Docker run command that I showed you before in the shell script. And the env section contains multiple environment variables with the same name that indicate versions of Spark I want to test against. Travis calls this a matrix variable or a matrix build, and it's smart enough to actually run my build one time for each one of those Spark versions. And voila, you're done. You authorize your repository with Travis, and you get a pretty badge and automatic builds every single time you commit, open a PR, or merge. And you get a sweet check mark on number 5. Finally, if you were to go to Travis for SparkPipe, you can see our full build history. And if you click through to a single build, you can see the whole process in action. You can even drill down into the results of individual tests. And I'm going to try to show you this. Oops. There we go. So if you look at this right here, here's a PR that someone opened recently. I'm going to stare at this screen so I know what I'm talking about. And if we drill down into any one of these builds, let's say the Spark 1.5.21, you can actually see the whole thing I was just talking about in action. Here's where it's extracting all the environment variables. There's the Docker run command, pulls the image, builds my code, builds my code, builds my code, builds my code. Runs my tests. Very exciting. There's colors and everything. Submits my code coverage report to coveralls, and we're done. And that particular build is marked as good to go. All right, back into this now. And we get our little check mark on number 8 because everybody can see the results of all of our builds in real time. As far as next steps go, I want to rebase Sparklet on the Alpine Linux base image. This is a transition that the Docker community is doing themselves. This should help speed up the build even more because it'll make the container a lot smaller. Docker Compose. The way I'm using Docker here is a little bit of an anti-pattern in the sense that the workers and masters should each be inside their own containers, and you should use Docker Compose to link them together. But there's an interesting trade-off there in terms of simplicity that's worth talking about. As far as the Windows development environment support goes, it turns out using volume mounting on Windows is a bit of a bitch. It doesn't work very well. So I'm trying to find some workarounds for that in terms of like dealing with paths and stuff, but nothing yet. And that's just for the development environment use case, so it doesn't affect your CI system because that's probably running Linux because you're using the Docker container. And Python. So the approach I've described here is for Scala, but nothing I've really described here is super dedicated to Scala. All you would really have to do is re-implement some of the build stuff using your Python build tool instead. And if you have any questions, feel free to ask them now. There's some important links at the top if you want to look at some of the stuff that I've done, because we have open source working examples of this actually taking place in the cloud. Feel free to contact me later as well. I'd be happy to help you set this up for any of your own projects too. Thanks so much.
I have a question over here.
I was curious if there was any particular reason you chose to go with Gradle over SBT.
Not especially. I think my company has a lot of familiarity with Gradle because we write a lot of Java projects that aren't Spark related as well. So it was kind of a natural transition for us to make, or rather lack of transition.
So this mainly, seems great for Spark batch stuff, but do you have any thoughts on how you would use this in a sort of streaming environment or anything like that?
That's a really good question. I suspect you would have to create a test suite that actually emulated a stream of data. But you could certainly apply the same approach to using a Docker container to contain the Spark cluster. I haven't tried it yet, though, but I will be trying it soon because SparkPipe will have some streaming-related operations before the end of the month. Anybody else? Oh, over there on the left.
So what about the data you use for the tests? Are they different from your local environment to the pre-prod?
Sorry, is what different between my local?
The data that the tests use?
They're generally identical. So when I'm testing in my development environment, I actually use the same container as the one that runs on Travis as well. I find that simpler. So one thing you can do with Docker is you can run a container in interactive mode, which allows you to start up a bash shell. And I can just run it one time, have my shell, and then type Gradle W test every time I want to test my code as I'm editing it in like my favorite IDE of the month or whatever. So what that really permits me to do is have really good confidence that the tests that I'm running are going to run the same way on my own machine as they're going to run in the cloud. And I find that a lot easier. I also find it easier than kind of downloading and installing new versions of Spark all the time. It's nice to just pull a container and turn it on and then turn it off again.
I think I should have been clear. What I meant is like the test data that you use for the
the test data.
Yeah.
Oh, sorry, I didn't catch that part.
Yeah. So
yeah, okay, good question.
What I'm trying to understand is like, what is the benefit of you get by running it on the cluster? So is it the reason why you run it on the cluster? Is it like the data is massive?
Oh, no, not at all.
Okay.
So I think one of the reasons is more philosophical than anything else. I don't actually think you're doing CI properly if you're creating a Spark context in your ScalaTest suite. Because of number 6 on that list of best practices that I talked about before, it's not really the same as running it in an identical production environment. But the other advantage is actually subtler, which is that if you do that first kind of practice where you create the Spark context in your ScalaTest suite, by default, it's not going to behave exactly the same way as a real Spark cluster. So a really good example is another library I was working on makes heavy use of accumulators. And accumulators, they have this merge code, right? When they go between the temporary results on 2 workers and then they merge together. Those code paths weren't being executed by default because when I was using the first approach, the one where I created a Spark context in my test suite, all my RDDs only had 1 partition because it's equivalent to like a single node cluster. And so I can fix that by going in and saying, manually partition this RDD into 2 partitions instead, and then the code path gets hit. But I'm still breaking rule number 6 of not testing in a production environment. Now, when it comes to data, that's a really good question. So in the case of my library, because I'm just dealing with general Spark operations that manipulate information, I don't necessarily have to test it on big data. But if you're trying to test some kind of script that is, of course, dealing with production quality data and all that kind of stuff, I would recommend that you extend the Sparklet container and actually bake in some sample data right into your version of the container as well. And that might make it easier for you to test with some real domain data that matches what you've got. Any other questions? Over there?
Okay, so you showed how you use Docker to create the Spark environment, which was similar to production.
Yes.
But there are other elements, right? Like if your Spark job needs HDFS or S3 or something like that. So how do you deal with those?
That's very true. So in my case, this is sufficient because the library isn't really taking advantage of HDFS or anything like that. But I think that the same rule holds. If you need to be testing code that is using that environment, then you should create that environment using Docker. And it's not a particularly difficult thing to do. And I would highly recommend it. I think it's made my test suite something I'm much more confident in. I don't really like to rely on the idea that testing my code with Spark inside my tests is the same as running my tests inside Spark. I'd rather treat Spark as a black box. And I think good testing practices really do recommend that. But yeah, definitely set up HDFS or something in the container as well, and you'll be off to the races. All right, cool. Oh, sorry, one more.
Yeah,
over here.
one more question, please.
Yeah.
How would you compare that to just instantiating the entire thing on Mesos and having, let's say, a small environment there for testing?
You mean like running it on a single cluster?
Yeah.
So I wouldn't recommend that, only because I do really think that you need to be running your tests on a fresh cluster on which you can guarantee nothing else is running. That's also sort of a philosophical point more than it is a practical point, but it can definitely influence your tests. For example, if 2 people commit to individual feature branches at the same time, both test suites are going to try to execute on that cluster simultaneously. They're going to need to share resources, and you're not really treating the tests as like a kind of clean room, if you will. So I would still recommend having Dockerized containers with Spark clusters instead. Of course, you're going to run into an issue if you need a bigger cluster. Travis, for example, limits the amount of RAM on their machines to 2 or 4 gigs, I forget. So you can't really test with really, really big data. And if you need to do that, I would recommend using Jenkins or Bamboo instead, and actually having a Docker host environment set up either in the cloud or on premises where you have more RAM available to your containers. But yeah, I think the advantage is really being able to say, these are the only tests running on this cluster. This cluster is brand new. Everything will be as it should be, you know, 7th day he rested kind of thing.
Okay. You run these tests on a separate machine inside the Docker, and the Jenkins is just starting that on the remote machine, or is Jenkins running on the same machine like the Docker contains?
Right, so we're not using Jenkins for this project. We're using Travis, but the philosophy is the same. So when I push my code, there's a commit hook that Travis picks up. It says, oh, hey, there's some new code. It pulls the code down, it builds the container, or pulls it actually, because our container is on Docker Hub, so it's our pre-build. So it pulls the container down, it starts the container and mounts the code into the container. Once it's reached that point, it can start the Spark cluster, compile the code, run the tests. And then the container gets shut down at the end of the test suite, and the exit code of the container actually matches the exit code of the test. So if the container fails, it means that your tests fail, and then Travis picks that up and says it's a failed build. You can achieve almost exactly the same thing with Jenkins as well. So the way Travis works is that it's essentially this gigantic cloud of tiny Linux VMs that Travis supplies in the cloud. So they give you one, and it's free for open source projects, which this is, so I didn't have to pay, which is fantastic. They give me one every time I make a commit from their big cloud of available machines. It does exactly what I just described. So the Docker host is the VM that's running my tests, and then it just gives that VM back to the cloud for someone else to use afterwards. Cool. Anybody else?
All right, excellent. Well, if you don't have any more questions, let's give another round of applause.
Thanks, guys.